Okay, as promised, we're still talking about logarithmic functions and specifically finding the derivatives of logarithmic functions. That's really what this is about. But this time we're going to recall laws of logarithms and see how we can make finding derivatives easier in some cases if we apply these laws in advance. So let me remind you what those laws are. There's three of them. Only three. Don't make any up. Okay. The first one is specifically called the product law, and it's about finding the logarithm of things being multiplied together. That's why it's called the product law. Of course, it could be base E, it could be base 2, it could be base 10, it could be a lot of bases. We're specifically interested in natural law where it's base N, base E, but we'll do it more generally here. So the logarithm of a product is the sum of the logarithms. That is, it's the logarithm of the first factor plus the logarithm of the second factor. And I know you're familiar with these, or at one time you were familiar with them. Now remember, M and N can be numbers, they can be letters, or they can be complete expressions. See, M itself might be the square root of x plus 1. N might be the quantity x squared plus 1 all to the fourth power. So there's no telling how complicated M and N are. The second law is called the quotient law, and quotient, of course, has to do with fractions. So it's about how do we take the logarithm, or what's a law pertaining to the logarithm of a fraction, of a quotient. Well, the logarithm of a quotient is the difference of logarithms. That is, it's the logarithm of the numerator minus the logarithm of the denominator. And once again, this M and N can be numbers, single letters, single variables, or whole expressions themselves. And the third of these laws is the logarithm of a power. That is, of course, we're talking about base B here. If we have the logarithm of some expression, a letter, a number, or even an expression to a power, P, then we can bring that P out, remove it from a power position to a factor position that's in front of the logarithm. So what we're taking the logarithm of is simpler. That's what it boils down to. In all these cases, we're taking the logarithm of things that are more simple. Now, let me, in a college algebra class, I make a big deal of this. Note what is not said. See, note that there is no law. There is no law for the logarithm of things that are being added together or subtracted. See, over here we have logarithms added, but not the logarithm of things added. So there's no way for us to deal with this. Okay, we cannot simplify. We can't simplify if we have inside the logarithm things that are added or subtracted. And that's what I meant by don't make one up, because there's nothing that tells us how to do that. Okay, so if you recall the first function that we looked at, see, we first considered this function f of x is equal to the natural log of 2x. And very specifically right here, the first law applies, because 2 times x is like an m times n. So what we could do for this problem, let's just come down here, what we could say is, oh, well, look, we can use law number 1 above, the first law above, and say the law of a product is the log of a product is the sum of logs. That is, we could take the logarithm of the first factor 2 and add the logarithm of the second factor x. Okay, and now that we've done that, here's how we would find the derivative. Okay, f prime of x, well, that would mean we'd have to find the derivative of the right side, which is 2 parts. So we'd have to find the derivative of the natural log of 2, and then add to that the derivative of the natural log of x. Okay, now of course finding the derivative originally wasn't too bad anyway, but this is to illustrate what's going on. Now, how we can apply these laws. Now here's what I need you to recognize though. The natural log of 2 is just a constant. See, the natural log of 2 is a number, not a variable. It's a number, a constant. It is a constant. In fact, if you put it into your calculator, the natural log of 2, your calculator will come back with something like 0.69314718. You know, it goes on forever. I mean, it's a non-terminating, non-repeating decimal. So that's the reason I put approximately equal to. But it's just a number, isn't it? And of course, the derivative of a constant is 0. And so there's no real work there. And we might have recognized that in the very beginning. And what we started out with is that the derivative of natural log of x is just 1 over x. So here we get 1 over x as our result, which is what we got a little earlier. Now, this is a simple application of that, but in some of our other examples, then this makes things easier. And so let's continue looking on the next page at another example. Okay, I think this is the third problem, or the last problem that we did in part 1. We were given the function f of x is natural log of square root of x plus 1, and we were to find the derivative f prime of x, and we did. Along the way, because the way we do logarithm derivatives is that we had to take the derivative inside, which meant we had to take the derivative of x plus 1. And so it became rather tedious. We got through it okay, but it was just quite a bit of work. So let's see how, as I promised, that there's a way by using laws of logarithms to make finding this derivative a little simpler. And here's what I mean by that. Let me write down the function again right here. And let me remind you, before we find the derivative, let me remind you that we recognize that square roots can be written as powers. So we'll write this as x plus 1 to the power 1/2. Now, when we do that, the third law of logarithms over there applies. The third law, remember that says if you have an expression to a power on the inside of the logarithm, you can bring the power down in front and then just have a logarithm of the expression without a power, with just a power of 1. And so we've actually made our logarithm look much simpler, and so it's going to be much easier to find the derivative. Okay, well now we're ready to find the derivative. So f prime of x, well let's see. 1/2 times a function is 1/2 times the derivative of the function. So all we're really doing is worrying about the derivative of logarithm of x plus 1. Now when we do that calculation, remember the way we do the logarithm derivative, it's 1 over the argument, so it's just 1 over x plus 1 without a square root on it at all, and then we multiply with the derivative of the argument itself, which we can determine without even writing this down that that derivative is 1. So we end up with 1/2 times 1 over x plus 1 times just 1. Well, the times 1 is not changing anything, and so we end up with multiplying 1 times 1 together on top and 2 times x plus 1 on bottom, which is exactly the same result we got previously, and I'll let you choose which way was easier. I think this. So we'll make sure that we try to apply this in other cases. Now, let me point out before we look at another example. We are going to look at an example here, but I'm not really going to complete it. Okay. I think we had y is equal to the natural log of 2x squared plus 4. And this probably isn't the best example here, but I'm going to use it to illustrate what I want to say. Find the derivative. Now, above, we found rules of logarithms, or laws of logarithms, a law of logarithm. Well, let's simplify that a lot. But see, in this case, no laws of logarithms apply. See, the exponent that we have here is on one part of the whole argument. And laws of logarithms don't apply. My bad. Kind of talking right at the same time. Causes me trouble every time. No laws of logarithms. Well, I really messed it up, didn't I? No laws of logarithms apply, or that is, I guess I had it correct the first time. No laws of logarithms apply in this case. And back to what I was trying to say. The exponent 2 has to be on the argument itself, not a part. It has to be on the parentheses that make up the whole argument. So that 2 can't come down. We can't get to that 2 because it's tied up with a plus sign. And because we have a plus sign, we can't break that apart any. Now, so we would have to do this the hard way. We must use the long way, as we did the first time. Okay, so because we can't say logarithm of 2x squared plus logarithm of 4. That's not true. We can't say that because we don't have a law that allows us to do that. So we're kind of stuck doing it the long way. Now, I'm not being completely forthcoming here. You know, the way it stands, we can't use the laws of logarithms, and that's why I said this probably isn't the best example. But, well, if you notice that this does have a common factor, that argument has a common factor of 2, we kind of saw that earlier on. So we could actually take that 2x squared plus 4 and write it as a 2 times x squared plus 2. Now, that's not going to be real helpful to us, but we could write that then as a logarithm of 2 plus the logarithm of x squared plus 2. So we could take that step. And then if we found the derivative of y with respect to x, of course the derivative of the natural log of 2 being just a number is just 0. And when we find the logarithm, the natural log of x squared plus 2, that would be 1 over x squared plus 2. And then we have to multiply that with the derivative of x squared plus 2, which is just 2x. And so the 0 in front doesn't apply, it doesn't help any, and we would just have the 2x times the fraction, so it'd give us a 2x squared over x squared plus 2, which is the answer we got earlier. It really didn't help us a lot in this case. The main thing I wanted to show you is because there's a plus there, we couldn't deal with this like we did the other one. Okay, let me catch my breath and see where we are. I think maybe I want to start, I think I want to start a third part. Let me look at the notes that I'm using here to see whether I do want to start a third part. I think I want to start a third part. So I'm going to end this one. We'll start up with a third part that will have some more issues that we have to deal with.